Okay, so I have a couple of more topics to round off this week. Um, and yeah, I'm just going to do that in this video. The first one I want to talk about is something called multipole expansion. Um, Again, because of time constraint, we won't be able to do too many problems in this, even though it's a very interesting thing to work out. But I just want you to be aware of what multipole expansions are. So even though we won't delve too much into problems, I just want to include this in the video. So if you ever hear about it, you know what it is. And it's kind of a generalization of what we did with the dipole approximation, right? So in a dipole approximation, we said that we forget all the internal retardations within a system of charges, and then we take like one common retardation. Now that's an approximation, and of course you can do a little better than the approximation, where you take into account some retardation inside the system, and then you can keep making it successively better, and then you can get kind of an infinite series where the more terms you add in the series, the more accurate your answer becomes. And that's what the idea of a multipole expansion is. So I'll quickly go through it. And again, we won't have time to delve too much into the details, but I just want to set it up so you're aware of what it is. Okay, so the problem is we have a bunch of charges, and again, it's a classical problem. Like, how do you know the fields given the charges and their dynamics? Let's say we start with finding the magnetic field, and I just made this choice because the B field just depends on A. There's no phi there, so it's just simpler to calculate. So the vector potential A is given by this equation. You know this already. It's the solution to the vector wave equation. And of course, all of this has to be retarded, right? And so we do the same trick where we introduce an extra integral where there's the integral with volume, which we always had, and now there's an integral on time. And then we have this delta function to take care of the retardation, right? Now, what I'm going to do now is actually take the Fourier transform of this expression. And the Fourier transform is going to be taken on the time axis, right? So I'm going to take the Fourier transform of the left and the right hand side with respect to time t, okay? And so I get A of omega on one side. So that's the Fourier domain representation. And that's just the definition of Fourier transform. So what we're doing is we're going to multiply by e to the I omega t dt and integrate on both sides. Okay, so now we have three integrals on the right, the one on the volume, the one on the retarded time t prime, and now the new integral for the Fourier transform. And as you can see, we can actually do the integral over t. Now remember that integral over t is not the same as integral over t prime. They are not the same variable. So you can actually push through the integration over t. And what ends up happening is you just basically replace t by the value which the delta function suggests, which is just t prime plus r minus r prime divided by c, right? So you get those two terms, e to the I omega t prime, e to the I omega r minus r prime by c. Okay. Okay, so that's just basically the Fourier transform, right? That's what we just did. Now, notice that there's no Jacobian here because in the previous derivation, we had the Jacobian because we didn't have a simple function. We had a function of r, and so you need a Jacobian there. But here the integration is over t, and so here we just have t. We don't have some function of t, right? So we don't have to worry about any Jacobian when we do the integral to get rid of the delta function. Okay, so you end up with this. Now, so we're going to play the same trick again here. So we have r minus r prime over here. So that's the distance between the source and the observer. And then the point becomes, okay, how am I going to express r minus r prime? And I can always do that, approximate that by saying r naught, which is a common distance to the center of the charge distribution, minus n hat, which is the position vector from the source to the observer, times r prime, right? And so this is just an expansion of the distance over there. Now notice that we are here assuming that you're very far from the charge distribution, right? So we are making that assumption that you're not very close to the charge distribution, we are very far from it, such that this approximation is valid. And so you go through that approximation, then you basically The R naught you're going to pull out of the integral, so the R naught just comes out of the integral, and then the n dot R term basically remains. And now again, now is when you do the series expansion, you write e to the ik n hat times R prime as a series expansion, okay? And that is just the series expansion for an exponential. And so you get the final expression where the whole thing is expressed as an infinite series. And if you take the n equal to 0 term, you get the dipole term, and that's the dipole approximation, which we already worked with. You take n equal to 1 term is called the quadrupole term, and so on, right? And so every successive term you add, you get closer and closer to the true answer, where you have taken care of the internal retardations in the system. And the internal retardations in the system are basically taken care by this factor, right? So n hat dot R prime is basically the amount of distance projected along the sight line to the observer. So this is basically measuring the internal retardation. K is just 2 pi by lambda. So this whole thing is the phase, the amount of phase that each particle is retarded by. And so when I take n equal to 0, I'm just equating all of that to the same value, right? So I'm just saying all of that is 1. That means that all particles have exactly the same amount of retardation. And so as I take higher and higher order terms in n, I get closer and closer to the true retardation between particles. Okay, yeah, so like I said, unfortunately, we won't do too many problems on this, even though it's interesting, because we just don't have the time in the course to do everything, but it's good for you to know what this is in case you encounter it later on in your research, for example. Okay, so the next topic I want to talk about is a very important one for this course and in general in physics, and that's the topic of Thomson scattering. And so Thomson scattering is just the scattering of radiation by free electrons. Okay, so you have an incoming electromagnetic wave, and there's an electron, and so you've already learned that there's a Lorentz force on the electron because of the varying electric and magnetic fields. The electron moves. And now in this week, you have learned that if the electron moves or accelerates, it's going to emit energy, right? It's going to emit its own electromagnetic field. So you basically have a situation where there's incoming electromagnetic field and there is some emitted electromagnetic field. So you can think of it as a scattering problem, right? So just like in classical, scattering, you have a photon coming in, it scatters over some particles, and then there's another photon emitted and so on. You can think of the electron as intercepting some of the energy of the incoming electromagnetic wave, and then kind of scattering it out, throwing it out as its own radiation field. And the problem here is to calculate how much of that energy is intercepted, right? How much of the energy gets scattered. And the general physics talk for doing this kind of problems is to talk in terms of cross section. So you basically say how big does an electron look to an electromagnetic field, and we call that the cross section. And if the electron looks bigger, it means it intercepts more energy, it scatters more energy, right? So that's what we're going to calculate. We're going to calculate the effective size of the electron as seen by an electromagnetic wave. Okay, so that's what we're going to do. Now, to do that, we're going to first show that there's no work done on the electron by the electromagnetic wave. And the reason why we're going to do that is, if that is true, then things become very simple in that you just find out the amount of energy emitted by the electron, right? And just use energy conservation. If that much energy is emitted by the electron, that much energy must have been removed from the incoming electromagnetic wave, because there was no work done by the wave and energy has to be conserved. Now, why is there no work done by the wave? We'll actually go through it. We're going to formally show it. So here's the equation for the Lorentz force on the electron equal to the charge times the electric field of the electromagnetic wave in this case. And this is the magnetic term. Again, we're going to assume that the electron is not relativistic. So V by C is far, far less than 1, and we're going to get rid of this term. So you just get with mass times V dot, which is the acceleration, is equal to charge times the electric field. Now, let's say we take a plane wave, right? We can always express free space radiation as a superposition of plane waves. So I'm going to just take one plane wave and see what happens. So I'm going to say that the electric field is along some unit vector E. E naught is the strength of the field, and that is just the complex harmonic for the plane wave. Now I'm going to plug that in here, and again, I'm going to just be working in harmonic space, so in Fourier space. So V dot, which is a time derivative, just becomes minus I omega times V, equal to, and that's just the plane wave, right? So you get an equation for V immediately. So the equation for V is, just take minus I omega on the other side, and you get an equation for V. Now, the rate at which work is done is force dot velocity, right? So the rate at which work is done, so this is ergs per second here, is just the force, which is q times E dot the velocity, which we just solved for. Okay, so I'm going to now take the real quantities. I mean, this is a harmonic representation. The velocity cannot be imaginary. The field cannot be imaginary. So I'm just going to take the real quantities. So for the electric field, the real quantity is cos of k dot r minus omega t. Now for the velocity, because you have an I here, the real part of this quantity is going to be sine of this quantities, k dot r minus omega t, right? And now you're going to see why the work done is zero. The reason the work done is zero, well, actually the work done is not exactly zero, the average work done is zero, right? Because if I now take the average of this quantity and call it total work done, this is the rate at which work is done. So I'm going to integrate over time. I'm going to accumulate that rate over time and call it the total work done in one cycle of the electromagnetic wave. So you get cos times sine. And if I integrate cosine times sine over one full cycle, you're going to get zero. And so what's happening is in part of the cycle, the wave is doing work on the electron. And in the other part of the cycle, the electron is doing work on the wave, or let's say the wave is doing negative work on the electron, right? And the net result is there's no average work done in an average sense, even though at an instant there is work being done. Once we average over the full cycle, the work goes to zero. So now we can apply energy conservation in that average sense, right? So the work is zero for a time scale far, far greater than 1 over the frequency. And notice also that for this to go to zero, the argument of the cos and the sine must not be zero. So k dot r should not be equal to omega t. What happens physically if that is the case? Well, if k dot r is equal to omega t, then that just means that the electron itself is moving, its r, its position is changing such that it's riding on top of the wave, right? So the electron then never sees the wave because it's moving almost close to the speed of light. It just sees an almost constant electric field, right? It's riding on top of the wave. It never sees the wave oscillate, because as the wave oscillates in time, the wave is also oscillating in space, and the electron is just riding on top of a wave. And so it basically never sees an oscillating field, at least approximately. I mean, the electron cannot be moving exactly at the speed of light. That's not allowed, but it can be close to the speed of light. So we assume that none of that is happening, right? So none of those crazy scenarios exist. And in that case, okay, so the average work done is zero. Now I can make the statement that the intercepted energy is equal to the radiated energy. Now let's calculate the radiated energy. All we need is the acceleration to do that. So V dot. And so we've already solved for that. So that's good. We know what V dot is. And the power radiated, which is ergs per second, is just this expression which we derived this week, right? So it's 2q squared by 3 zeta beta dot square. You just plug in V dot here, and you're done. That's basically the power radiated at any instant of time, right? Now again, I can look at a few terms here, and it's good to define a few terms here. So the first term which I want to define is given by q square divided by mc square, okay? And that is called the classical electron radius. What is the physical interpretation of it? We can give a physical interpretation in the following way. Let's say I take mc square to the other side and bring r naught here. Then on one hand, I have mc square, which is the rest mass energy of the electron. And on the other side, I have q square divided by r, which is some measure of the potential, electrical potential energy of an electron. So if you have a sphere of radius r and the sphere has a charge q on it, then its sort of electrostatic potential energy, so the amount of energy or the amount of work done to assemble that sphere from infinity, is going to be of the order q square by r, right? And so this classical electron radius is that radius which you have to assume that an electron has. If you picture the electron as a sphere, such that its electrostatic potential energy is just equal to its rest mass, okay? And that's why it's called the classical electron radius, because it is just a classical description of how big an electron appears in electromagnetic calculations. That's just the size of the electron. And again, I want to stress here that it's not the physical size of the electron. This is just, think of it as a figurative interpretation. It's not, I'm not claiming here that the electron is actually a sphere. It's not actually a sphere, but it's a classical picture that helps you to understand the cross section of an electron to electromagnetic phenomena. It just so happens that the length scale, which appears again and again in electromagnetic calculations, is this length scale. It is the length scale where if the electron had that size, its electrostatic potential energy would be equal to its rest mass. So, you know, that's an interesting thing in itself, that that length scale keeps appearing in many calculations. It just tells you that that is an important quantity that tells you how big an electron appears, even though it physically is not. Okay, so I'm just expressing everything in terms of the classical electron radius because I have at least an intuitive picture of what it is, what it means, okay? And now I want to know how much energy is being taken away from the beam. So I know how much power is radiated. So now I want to know how much power was incident. And then I know what fraction was taken away and I get a cross section. So I'm going to write the incident Poynting flux. Again, we derived this week. So you know that is the expression for Poynting flux. And so the cross section is just the radiated power divided by Poynting flux, right? So on the top you have ergs per second. On the bottom you have ergs per second per square centimeter. And so if you divide the two, then you get what was the cross section, what was the centimeter square cross section, which would take this amount of Poynting flux and result in this amount of radiated power, right? And so that cross section I'm going to call sigma, and it works out to be 8 pi by 3 times r naught square. And that is called the Thomson scattering cross section. Notice a few interesting things. It doesn't depend on frequency, right? There's no omega naught, there's no omega there. It doesn't depend on the strength of the electric field, right? So it doesn't depend on the incident power. It just depends on R naught, which is composed of a bunch of fundamental constants. So the Thomson scattering cross section is, it's the same value at all frequencies, at all energies. You can treat this literally as a constant of nature. I mean, some of you who've done quantum theory know that, there are exceptions to it. This is just a purely classical treatment. And even in the classical treatment, we have made a dipole approximation, right? The radiated power, this expression for radiated power, assume that the electron is non-relativistic. We got rid of, many terms. We said beta is almost equal to 1, kappa is almost equal to 1. Anyway, in that approximation, you can make this statement, right? In reality, of course, it's not true. I'm going to give you a problem in the problem sets where I ask you to derive what is the next correction term that must come in here. What is the next term in the Thomson scattering cross section? And you'll see that that term actually depends on the frequency of the wave. It depends on the amplitude of the wave. And so that dependence will be through something called as a laser parameter, which some of the physics students might have encountered. It just is a measure of how strong the field is, the electromagnetic field is. Anyhow, so that's basically Thomson scattering. And the way to think about Thomson scattering is the electron looks like an aperture of this area, and any energy falling on that aperture is scattered by the electron. Okay, it's taken in from the incoming beam, it's subtracted from the incoming beam, and it is scattered in the form of dipole radiation. So whatever energy was coming in let's say, imagine a beam of energy coming in, that energy is subtracted from the direction of the beam, and then it's emitted in the pattern of dipole emission. And so that's basically at the heart of what Thomson scattering is. The last thing I want to do is actually give you a pictorial representation of why accelerated charges radiate electromagnetic waves. and we went through a formal derivation with delta functions and Jacobians and all of that. But I really want you to have the physical intuition, so you understand what is really happening here. And it's important for you to learn both. You have to go through the hard algebra to make sure that you get the right answer. It's very hard to get it's very easy to make mistakes just doing it, like back of the envelope, physical intuition kind of way. But you also need to have that physical intuition to actually grasp the physics of what is happening. So I want to give you both. So I gave you the hard stuff first. We got the hard stuff out of the way with the derivation of the retarded potentials, the fields and all of that. So now let's do the fun stuff here, where we go through the physics of it. So imagine a charge at rest. Okay, and these are the electric fields of the charge. They're just going radially outwards. I've just drawn a bunch of lines for simplicity, but the main point is they all go radially outwards. Now assume that I give the charge a jerk, right? So I move it impulsively, and I ask the question, what's going to happen when I move it impulsively? Okay, because information can only travel at the speed of light, close to the charge, that information has already traveled, that the charge has been suddenly moved by me, right? And so the fields close to the charge again have that radial structure, right? They're all going radially outwards. But away from the charge, that information has not reached yet, right? So away from the charge, the electric field behaves as if the charge were still in its original position at rest. So away from the charge, you have the electric fields all pointed radially outwards, from as if they were emanating from this point here at the center. And so in some intermediate location, the field lines have to be continuous. You can't have a field line that just ends in vacuum. So at some intermediate location, the field lines are going to connect, right? And that location, that radial distance where those field lines are connecting, is going to move out at the speed of light. The whole thing is going to expand at the speed of light as the information propagates of the new position of the charge at the speed of light. And that is the radiated electromagnetic wave, right? That is the radiation. It's moving out at the speed of light. And notice how it's also transverse. There is a transverse component of the electric field. And before, when the charge was at rest, you only had radial component. You never had a transverse component. And now it is the transverse component which is moving out at the speed of light. And that is the radiated electromagnetic field. And that's why it is a transverse electromagnetic wave. And so that's kind of the physical intuition. Now, what's really fun about the physical intuition is all the messy derivation we went through can be very simply arrived at with just this simple geometric picture. And I want you to show that because it's fascinating. So just imagine a single field line. So, in the previous graph here, I drew a lot of radially emanating field lines. I'm just going to take this field line, right? So I'm just going to take a single field line at some angle theta. Here's the old position of the charge. Its velocity was 0, and I'm going to call the time equal to 0. And then I decided to give it a jerk, and I decided to move it by velocity delta times v. And let's say that I did that in an infinitesimal amount of time, delta t. And then I'm going to now look at this picture at time t afterwards. Okay, so delta t was the duration over which the velocity went from 0 to delta v. And now I'm going to look at this picture at a time t. Okay, so at time t, the information of the new position of the charge has basically traveled a distance c times t. Okay, so until out a distance of c times t, after the acceleration, you have basically a field line which is a field line which basically points to the new position of the charge. Now, at a time there is another a small interval of time delta t where the acceleration happened, and this is the field line corresponding to that duration where the acceleration actually happened, when v actually went from 0 to delta v. Okay, and so that is that duration here. And then all observers which are further beyond still think that the charge is at its original place. Okay, so that's the electric field. And what I want to solve for is this tangential, the theta component of the electric field, right? I want to solve for the tangential component. So I want to take this electric field here, and I'm going to decompose it into a radial component that goes out like this, and a tangential component that goes out like this. And I'm just going to use geometry here, nothing else, just plain geometry to figure out what that component is. Now, a few things related to geometry. This distance is delta V times t, because the charge is moving at a speed delta V and it has moved for a time t. And so this projected distance here is delta V times t times sine of theta. Actually, I'm sorry, that's a mistake. This should be sine of theta, not cosine of theta, right? When theta is equal to 0, that distance goes to 0. Theta equal to 0 is on this axis. So this should be sine of theta. I apologize, that's not cosine theta, it should be sine. So that's the length of this side of the triangle, of a right angle triangle. Now this length here in the triangle is just c times delta t, right? Because delta t was the duration over which the velocity went from 0 to delta v. And so that entire duration is encapsulated by the width of the pulse, if you may. This whole thing is expanding out. The information is going out at the speed of light, but the width of that pulse, the duration over which the electric field actually changes from this configuration to this configuration, is delta t, right? That's the tiny duration over which the acceleration happened. Okay, so that's plane geometry. So I want E theta, which is the electric field along this line here, divided by ER, which is the radial component of the electric field, right? I'm just solving this triangle now. I'm just solving this right angle triangle. E theta by ER is equal to that side of the triangle, which is delta V times t times sine theta, divided by this side of the triangle, which is just c times delta t, right? So that's E theta by ER. Okay, so what does it mean? E theta is equal to that factor multiplied by ER, and you know what ER is from electrostatics. It is just the charge divided by the square of the radius. That's the electric field of a point charge at a distance r, right? And so you get an expression for E theta. Now, R is equal to C times T, right? So T is just R by C. So I'm going to get rid of T here, and I basically have the expression I need. So E of theta, the tangential electric field, which is going out at the speed of light, is equal to Q divided by RC square V dot sine theta. Okay, and where did V dot come from? It's delta V by delta T, right? That's V dot. I mean, you can go back to your notes and check. That's the same as our previous result. That's the electric field radiated by an accelerating charge. It just depends on the acceleration and the sine of theta. It goes down as 1 over r with distance, and you know it has these constants q divided by c square. So all the blood, sweat, and tears with delta functions and all of that, you kind of get to the same answer, at least in the non-relative, in a very simple picture, right? Non-relativistic, we made all those approximations here. You kind of get to the same picture, and it's good to have both views. It's good to know this view, so you know the intuition of why an accelerated charge radiates. An accelerated charge radiates because special relativity is true, that the information cannot travel at infinite speed, and for the electric field to have continuity, you need to have a tangential component of the field that goes out at the speed of light, and that tangential component happens to go down as 1 over r. Unlike the radial component, which goes as 1 over r square, the tangential component goes as 1 over r, and those are the radiated fields of a charge. So that's kind of the physical picture you should have for why accelerated charges radiate energy.